Welcome all to Immersive Science in VR. You're joined by Rebecca Allen, and my name is Alan Duffy. We are sitting in Swinburne's Hawthorne campus, live streaming to an international audience. But we would like to start by acknowledging the traditional owners of the land upon which we are meeting, the Wurundjeri people of the Kulin Nation. We want to pay our respects to their elders past, present, and emerging, and extend those respects to all Aboriginal and Torres Strait Islander people across the nation, because this Science Week, we are going to many sites across the country, and I'm just looking at some of the latest that have been up. Thanks for joining us, Romsey, Bendigo,
Lalor, Canberra, even in UWA, we have, sorry, I read that backwards, guys. In West Australia, we have UWA Easy Zone.
Mm-hmm. And also in Lilydale, so Yarra Ranges Tech School, thank you for joining us. We have new people, new groups coming online, so we'll give you little shout outs as we go on.
Absolutely.
But why are they tuning in, Rebecca? What's the exciting thing?
So the reality is we're taking you on a virtual reality tour of our solar system and beyond. And we really want to share with you some of the amazing technology that is enabling us to make these incredible discoveries that we can't wait to tell you all about. How we have at Swinburne and with our partner astronomers have been just working so hard to reveal these incredible things about our universe. But real quick, I just want to tell you, because we want you to really enjoy this experience. For some reason, if you're having issues with the VR app side of things, you can always turn VR mode off and watch in just normal screencasts, I guess. So please follow along with us. Now, I think we should be ready to go, Alan.
Yeah, just a reminder that we want you to ask us questions throughout all of this. We have the hashtag #AskSciVR.
That's right.
Our team is monitoring. They will endeavor to relay those questions to us. It'll be really slick. They'll basically scream and I'll look down and I'll read the question out to you all. Wayne Garata, welcome. Thanks for joining us. That's going to happen a lot through this. So, I guess.
Oh, one more thing I wanted to say. This year, our theme was astronomy for all Australians, and we've really worked hard to make this experience as accessible as possible. Now, as you're watching the live stream, we do have closed captions, but this talk is going to be recorded, and we're going to edit those closed captions so you get our full story that we are so excited to tell you today.
That's right.
Okay.
Right. Without further ado, where do we go first?
I think we should explore our home in the Milky Way galaxy, our solar system. So let's go to the menu, which you'll notice you can see on your screen. And I just want to point out one quick control thing. On the top left of your menu, you'll see some arrows. If you click and drag those, you can actually move your menu so it's not blocking some of the incredible stuff we're going to be looking at. So now that we're in our menu, let's hop and click on solar system. Now you'll notice the first thing that jumps right out at you is our sun. It's massive, it's bright. We literally wouldn't be here without it, because all of the stuff that was left over from when our star formed is what we and our planets formed out of. But even better, all the stuff we're made out of either was born inside a star, or when stars died, or as we might talk about later, is how their remnants, when they're dead, collide in these extreme explosions.
That's right. Okay, now I'm going to hijack and take us to my favorite planet, which is Jupiter. So please go down and select Jupiter. If you, for you, it's over that side. Cool. I'm excited to see where Jupiter is for me. Okay, so for me, it's over this direction. So we're seeing the beautiful gas giant Jupiter. This is the largest planet in our solar system. There is a anticyclonic event, a storm that has been rolling around this giant planet for, we think, at least several hundred years, since Galileo first saw it in the very first telescope. Now, well, it's a bit sad.
You got to look out. Sorry. I was so listening to what you said, and then I almost got hit by one of Jupiter's moons.
We just introduced that this year. That's true.
But yeah, so we know from the Juno spacecraft that great red spot that has existed for at least hundreds of years, probably thousands of years, is disappearing.
Yeah.
So catch it while you can, because within the next 10 to 20 years, it could be gone.
Yeah, and we don't know why it's losing that energy. It's a bit of a mystery. We've actually seen it consume other storms and regain its energies.
Yeah.
Well, this time it seems to be on an enforced diet for some reason.
Yeah.
And it is fading away.
But never fear, when one vortex disappears, many more seem to be found. And Juno is discovering incredible ones at the poles of Jupiter. There's even the Abyss vortex. So much cool stuff that this spacecraft is showing us.
Nice.
But we don't live on a gas giant planet. We live on a rocky planet.
Mm-hmm.
And I think we should actually, if you're looking at Jupiter, turn towards the inner solar system and you'll see the sun, but you'll see all this debris in between us and those rocky planets. And that's the asteroid belt. So we have our sun, we have planets. I know
I got the moon. Yeah, the moon hit me.
And we have these other smaller objects that didn't quite make it to planets called asteroids. But let's jump now to Mars. So Mars is just on the other side of the asteroid belt. And it's much smaller than Earth, but we're so interested in it. Why is that?
Well, that's because Mars at this point appears to have the best chances for life beyond Earth, or at least once had life.
That's right.
We now know that because of the different structures on that planet, these carved canyons, strange looking, almost waterbed kind of features, well, thanks to this landers, the rovers that have been sent there, we now know that's exactly what it was. These were seas, rivers, all of these structures indicated that Mars once had water on its surface. And at least for us, where there's water, there's life.
There's life.
So we get pretty excited about that. And then everything went a bit crazy because in the last couple of years, the latest probes, the latest orbiters have actually now shown that there still exists water.
That's right. And so in this version of the app, so when you look at the planet of interest, look down, you'll see for Mars, we have a cool little explanation of just how cool this planet is, but you'll see two words that are highlighted there. So if you click on robot, you're going to get a close-up view of the InSight lander, which is now there again, going further and further with the scientific analysis. It's actually for the first time drilling down into the surface of Mars. It has a seismometer, which is telling us, is complementing that other information of the temperature that we might find out with, are there Mars quakes? Is it getting hit by an asteroid right now? And so it's really cool to be able to see that this planet that we thought was dead, it's red, nothing super interesting, might be active.
Yeah.
We're finding evidence that microbial life probably was there at one point, if it is not still there.
Yeah, that's right. There's emission of methane. This is a gas that on Earth is directly linked to microbial life, to cows farting. Basically, it's not impossible that it could be produced by the breakdown of rocks, certain types of rocks, but it's pretty amazing that we're detecting it on Mars. So that's one of the big breakthroughs. And we can also look to another highlighted word, which is the water. And that's in the text below the planet Mars. And this is one of the images that were taken of the Martian slopes. Those kind of gray, dark streaks that go down the mountainside, those lineae, they only appear in the Martian summer. These look to all intents and purposes like something is melting and then that water is cascading down the surface. Very, very cool, very exciting, because liquid water, albeit very salty, like it would absolutely pickle you if you try to drink it or even put your hand in it, but salty nonetheless. That's very exciting stuff, because that means, again, where there's water, at least on Earth, there's life.
Alan, I think we're doing a great job of sparking curiosity, because we have our very first question.
Wonderful. Okay. Ben from Canberra, thank you so much for the first question. Why do the larger planets spin slower than the smaller ones?
Ooh.
Oh, do you want to do it? Can I have it?
Yeah, go for it.
Yeah, okay, because I can do a bit of theatrics. Amateur
I'll
drama
lean
society
over
here.
a little bit.
So if you've ever seen an ice skater, a figure skater, would I be in shot if I did a seat and twirled around? Oh my gosh, okay. Grab me a seat. Okay, so when in doubt, when VR fails, do real life stuff. So, okay, so basically...
I get to spin you.
Yeah. So this is called conservation of angular momentum. I'm going to sit down. This might be, okay. So spin me fast. Okay, now I'm going around and ow, we did not demo this. And then I put my arms out and I slow the rotation down. Let's go the other way. So if you start to spin me with my arms out, and then I bring them together like I'm contracting as a planet, and I spin faster. Now, this is the principle of conservation of angular momentum. But in other words, if you are a big, I'm really dizzy now. If you are a big planet, you're going to be spinning more slowly than when you're shrinking and you actually have condensed in, and you'll speed up. And this is basically what happens when stars die. They become smaller objects, and those objects actually spin faster to conserve this.
That's right.
Having said that, it depends. It can be a little tricky because some of the gas giants, you actually have such incredibly fast wind systems that they can those pieces can be moving more quickly than on a rocket planet. So in principle, conservation of angular momentum always holds, but what you see of the planet spinning,
that's right.
We only just discovered what the length of a day on Saturn was.
That's right. And it's really
Cassini helped us figure that out, one of those latest technologies. But so thank you for the question, Ben. And Belinda at Helensville asks, will we ever live on Mars?
I think that's an excellent question. It's going to be very challenging because even to help our astronauts stay alive on the International Space Station takes a lot of resources and, continuous resupply. And when we think about the idea of even going to Mars, that we couldn't take everything that we need with us.
Yeah.
On the way, we would have to think about refueling, food supplies, and then what about just sustaining our bodies, because they tend to actually break down in this environment called microgravity, which means it's much, much less than the gravity we experience on Earth. Yep. So I guess the answer is maybe. I think we should try to work a bit harder on protecting the planet we live on now, but there's nothing wrong with being adventurous and looking to just what it would take to go to Mars and live on Mars, because I think we're going to get some wonderful science advancements from that as well.
Yeah, and some of those science advancements that can be in the water purification, right? If we say we want to drink that really salty water of Mars to save us having to bring it along with us, well, that technology can be used here on Earth for desalination to make drinkable water for us on Earth. Or we could look to the types of crops that grow on Mars happily. It's the potato seems to be the best. As an Irishman, I'm very proud of that. And we can make these potatoes that can grow in particularly arid conditions like the deserts of Mars, and we can use those in water-stressed regions on Earth. So again, everything we learn about the solar system going and beyond can often help us back here on Earth. Oh, and hello, Jinjin. Welcome. Thank you for joining us in Western Australia. I was there a few years ago. I love that Discovery Centre. It's great.
So Western Australia is cool, but we got to give a shout out Gold Coast and Queensland. Thanks for joining us as well. Well, Alan, I love the solar system, and we certainly have only skipped to a couple of the planets, and we encourage you to, in your own time, explore all of them. But we're making discoveries not just in our solar system, but beyond. So I think now we should press the home button on our menu, and navigate to the app called All Sky View. Okay.
All right.
Now, Alan, what are we looking at here?
All right. So this is a view that I hope is familiar to a number of you. This is our Milky Way, seen in visible light. You've seen this stretching along the night sky, I hope, above your heads at one time or another. We've rotated that so it's a nice flat disk. We're in the disk of our galaxy looking back across it, and that's why it wraps all around you. So with this optical image, we see countless billions of stars that have all blended that light together to give that nice little, I guess, that pale white coloring. We have the dark regions, which are the dust lanes that block that starlight of stars behind them.
And speaking of dust lanes, we paid our respects to the indigenous people that once were on this land before we were here, but they were also some of the very first astronomers.
Yeah.
And Alan, speaking of those dust lanes, do you want to describe one of my favorite features?
That's right. So this is described by the Gurungai people in Gurungai Chase National Park. You can actually find an engraving in the stone of an emu, stretched emu, very unnatural pose for an emu. And you sort of think, well, what's going on with that? And then at a very special time of year, that engraving will line up to this emu in the sky. And that is the dark dust lanes of the Milky Way, perfectly resembling that rock. And to be honest, once you see it described as an emu, it's really hard to see it any other way.
Yeah, I agree. And so, these peoples were finding patterns in the sky way before we were. And to kind of give you an idea of that, now these were more of our, European ancestors. But if you go down to your menu, you're going to see below the electromagnetic spectrum some tick boxes. And one of those is constellations. So if you tick that on, you can see some of these, again, first patterns that we recognize from this bright starlight. And so these constellations are great because they're kind of our map of the celestial sphere as we look up into the cosmos. But we're just kind of in optical light. So I think now we should explore what our galaxy looks like in other wavelengths of light. Because while our eyes are great detectors of optical light, there's so much more to be revealed.
All right. So if you go down to the wiggly line, and this indicates the electromagnetic spectrum, all the possible types of light that you can have. If you go all the way to the left, and this is to the radio waves, so very long, and click gleam, we get this incredibly beautiful image now. The night sky has changed. This is what the radio telescope, the Murchison Wide Field Array, sees in Western Australia. So to everyone at Gingin, you should all know this. This is just up the road from me in the Murchison Radio Observatory. It's like 1,000 kilometers. This is going to be essentially the first step, a prototype in what will be the largest radio telescope ever built, the Square Kilometre Array. It's incredible what you can see with this thing. Oh, Wagga Wagga, thanks for joining us in New South Wales. I got distracted by the sky. So we now can see the Milky Way. That light has changed. What we're now seeing is the glow, not from stars, but from the gas itself, heated and glowing bright. And in particular with this radio waves, you can also see the cold gas. It's very curious, the features that you can pull out. One object in particular I want to see is if you pan to your right, at least that's where I can see, and look up above the disk, you see Centaurus A. So this is a very strange structure. So we see there's these two, we call them jets, but basically there's a feeding black hole at the center of this galaxy, just over 10 million light years away from us, and it is busily munching on infalling gas, you name it. It's a bit of a messy eater, and it blasts a lot of that material out along these two jets along its poles. They're basically like blowtorches, carving out the intergalactic medium, stretching out to vast scales, and we can see them easily with our radio telescopes. But keeping it in frame, in sight, just start to click, and we're now cycling through all the wavelengths of light, and basically, you don't really see it in most other, especially in optical. It's almost completely invisible, actually. You just wouldn't be able to really notice anything. Certainly not those giant jets. So the incredible new telescopes that are here in Australia, they're really facilitating our ability to see new and exciting things like feeding black holes.
Well, speaking of black holes, I think we should now go back to our menu. And if you haven't already, switch off constellations. And now we're going to turn on special objects because we want to show you some monster black holes. So again, special objects. And I'm going to first switch to optical so I can find, right in the center of our galaxy, in the heart of our galaxy, lurks Sagittarius A.
Kind of projecting a little bit on it.
I know, sorry. It could be a really nice black hole, but probably not.
It's probably not.
Probably not. But if we find Sagittarius A star and we click on it, oh my gosh, what do we see? So now we're getting another one of these cool close-up images that we brought to you in this app. Look at that.
Yeah.
So much energy. Even though our black hole at the center of our galaxy is very, very massive, it's not technically in the feeding.
No, that's right. It's dormant,
So, but even then, we can see that there's so much heat and energy around it, but we still don't see it directly. And that's because of the nature of black holes, right? They gobble everything up. So we shouldn't be able to see one.
Yeah, including light, right?
Yeah.
Hence the name.
But what's just happened?
Well, we have seen one. So that's a zoom in with a radio telescope, Meerkat. This is the Square Kilometre Array Pathfinder in South Africa. Beautiful telescope, but not quite got the ability to see an actual black hole. So for that, should we break our necks to see this? Should we give people
let's give the kids something to do.
Okay. Well, look, you can change coordinate systems and make this easier on yourself, or you can just absolutely arch your neck, look Oh my gosh, right above your head. And there, keep clicking at M87 until it pops up. Oh, my neck. Right.
You can always lie down.
Yeah. You should be seeing this image. This is a black hole. Fundamentally, they're invisible. They consume everything,
That's
including light that gets too close. But this black hole, the gravity is so intense, it's actually wrapping the light from background stars around itself. It's wrapping itself in starlight, and that's the glowing ring that you can see. We took telescopes from across the world, radio telescopes, linked them together to see this picture. It's called the Event Horizon Telescope. The blackness in the center is actually the shadow of this black hole, 1 billion times the mass of our sun. But it's not actually a shadow like in the way that your hand would be in the way of a light. I'm casting a shadow right now. It's actually because the black hole has consumed all of the light that has gotten too close, crushed it, dragged it inexorably into itself, and crushed it at the center, the point where space, time, and all the laws of physics break down.
So I certainly don't think that that's a nice black hole. I think we can say
it's just doing its thing. I'm just saying, it's just doing its thing.
Just going along with nature.
Yeah.
But that's so cool that for the first time ever this year, we have a picture of a black hole.
Okay, wow. Okay, I have been really, Jackie, by all means, just shout out. I've been neglecting these questions. And West Wyalong in New South Wales, thank you also for joining us. Okay, so ask SciVR, use the hashtag #SciVR. You
guys are doing a great job so far. And we'll get to some more questions at the end, so don't worry.
Oh, wow. Okay. Well, you're an observational astronomer, so I'll throw this one to you. So Ollie from Gundagai wants to know, why do stars appear to twinkle?
That's a fantastic question. So one of the great things about Earth is that we have an atmosphere that provides oxygen that we breathe, and it also helps protect us from a lot of that radiation and icky stuff from space. But those dense molecules that are in our atmosphere are also really good at bending light, like a prism. And so when you have stars, especially ones that are close to our horizon, their light is shining through more atmosphere. So it's like they're going through a prism. And so that twinkling you see is from the moisture in our atmosphere, literally refracting and bending that light. But I kind of like it. I think, astronomers don't like it because that means it's very hard to get a nice, crisp, clear image. But I think it's quite beautiful because it has this twinkling appearance. And so that's another reason why when we build telescopes, we try to find places where there isn't a lot of atmosphere. So in the desert, high up on a mountain, these are the best places to get this crisp view of the sky.
Absolutely.
Thanks for the question.
All right. So I'll give you all a break. You can pan the camera down and we can just sit and stare at the horizon, at the galaxy.
Big shout out to our team here who are helping us.
Mark, great work on that. Okay. So yes, we've been joined by Gundagai who got that first question in. So thank you for joining us. This is a good question. I actually don't know the answer. So we'll throw this to our... So I should also point out we have a number of astronomers who are on these social medias who are also going to try to answer your questions. We don't get to them now, like this one, I suspect. But Bramjot at Lalore Library has asked, who was the first Australian astronomer?
Ooh, good question.
I don't know. I can tell you there's some famous Australian astronomers. Ken Freeman's pretty good. Nobel laureate Brian Schmidt's pretty good. I don't know who technically was the first, though, so we'll have to throw that to an online.
Well, I think I'm going to just, go for not what I call an easy answer. I don't mean to be disrespectful, but I think the indigenous peoples that were here.
Well, they're definitely the first astronomers.
Astronomers. But in terms of what we call modern astronomers, I guess that's a really fantastic question.
Yeah, I don't know the answer.
Probably a radio astronomer. Okay, well, we're going to put this to our team on social media to help you out. Thank you for challenging us. It's actually nice when we get a question we don't know the answer to because we're learning with you.
Yeah, that's right. Okay. Oh my gosh, Lalore Library, you're asking a lot of questions. Okay, one more. This is great. So Rimat at Lalore Library has asked, how many planets have seas?
Ooh.
So I don't think we're going to name them all, but there's an... Well, okay. In terms of seas that are open to the sky that we are familiar with here on Earth, one. It's us. In terms of bodies of water, so there's an underground lake in Mars we've just detected. Nothing on Mercury, I would suspect. We have nothing on Venus. That is just
too
a
hot.
nightmare zone. Going out, there are moons of Jupiter and Saturn.
Even more probable are the moons.
Oh, there's many more. Yeah.
Yeah. No, but that's we always think planets, and we think you got to be this big body to have water.
Yep.
But what we're finding, especially thanks to the amazing force that is gravity, is that around these gigantic gas giant planets, they're stretching and torturing these poor moons.
Man, you are really projecting today. What? All right, keep going.
No, but that gravity actually heats up the planets enough that they can have water. And we think Enceladus, for example, is what we thought was just a solid ice moon around Saturn, might have under the thick ice surface, might have oceans.
Yeah, subsurface ocean. In fact, many more of those than perhaps are open to the air like us.
That's right.
So we can't count those, but I think it's probably safe to assume under a dozen, maybe half a dozen worlds with water
in our solar system.
Okay.
It's a lot harder to answer that outside our solar system.
Final question before we move on, because there's a lot of the universe to explore.
That's right.
Chelsea has asked, what causes a black hole to form? We could cover that. Are we going to cover this?
Yeah, we'll talk about it. We'll talk about it a little bit. Oh, well, actually, what I was going to say, because we're not going to have time, but at the end of the talk, we're going to walk you through one of the assets where you'll get to see that, and you'll get to make your own black holes. And so hang tight with that. We're going to answer it a little bit for you now, but then you're going to get a chance to do it yourself.
Yeah. So very simply, just crush a lot of stuff into a very small volume. Eventually, its gravity gets so strong that it just runaway collapses, and it has an escape velocity. So that's how fast you have to go away from it to escape. And once that's more than the speed of light, it's by definition a black hole. So you could do this with the entire Earth. If you could somehow figure out a way to squeeze us into something about the size of a marble, then we would be a black hole too. Typically, naturally speaking, these things only occur when massive stars die. And that's what we will hopefully cover towards the end. Yeah. Oh, Rosny and Tazzy, thank you for joining us. Cool. All righty. So we're going to have to roll on.
Yeah. So we've looked now in our galaxy. So we're discovering all these incredible things. Yeah. We're taking pictures of black holes.
Not too bad. Let's be honest. Yeah.
But taking pictures of black holes is really hard.
Mm-hmm.
If we also want to study, how these massive gravitational influencers affect space-time, isn't there another way that we can do that?
Yes, that's right. You can directly detect a black hole, not just by seeing, but by hearing.
What?
So we are going to go and explore some gravitational waves. So I actually want to go to GW events. So if we can just pan down, click on that. So this is where we download the very latest colliding black holes, or at least objects that have been detected by gravitational waves, and we'll explain how you can do that in a little bit. But I just really want to point out how incredible this is. 5 years ago, I had never detected anything with gravitational waves. Today, you're going to click the button, show latest detection events, and it may take a few seconds for you to load. That's actually going to the gravitational wave discovery centers and asking, well, what have you seen recently? And if you look on the ID, so these are our horrendous kind of telephone numbers. It's basically the year, month, and day, and then some other little information. Basically, in the last couple of days, and in particular, it's S190814. This is already going to be out of date, by the way, by the time I'm sure anyone watches this in repeat. But there's something that has happened, which we have been waiting years to see. It is a neutron star black hole collision, a binary.
That's so cool.
Oh my gosh.
Just in time for Science Week.
Yeah, it was well-timed object. Thank you so much. It was 250 megaparsecs. So, oh gosh, that's awkward. 750 million light years away. A collision between a neutron star, the crushed dead heart of a massive object, and a black hole, the crushed dead heart of something even bigger, have collided. And in that action of being torn apart in the collision, gravitational waves have been released, and we'll show you how that happens. But also, we hope the emission, the glow from that collision, and that's very exciting. That's what we're hunting for right now. At the time of this, we have not yet, but we're looking. That is incredible. So I'm really pumped.
That's
about
amazing.
It. Like this just happened for Science Week, so well timed, by the way.
Not just one black hole, but a black hole and its companion smashing into each other so far away that it takes the, if there were any light emitted around that area, it would take it, hundreds of thousands of years to reach us.
Oh, well, in this case, this particular example is 750 million light years, right? So I don't even know what the Earth was doing at that point. Were there dinosaurs? I don't know. Okay, but there are other objects, and in particular, the 1907-27 black hole binary. So two black holes slammed together. Because they're black holes, they don't shine. When they collide, they definitely don't shine. So how do you detect them? Well, gravitational waves. So
just how do we detect gravitational waves?
Yep.
Now, before we jump to it, I just want to say we're using this term gravitational waves. Where did that come from? Well, this is something that Einstein predicted because he worked so hard to describe how gravity and space-time have this relationship together and how mass affects space-time and how space-time then curves and affects us in it.
Yep.
And so he, had this idea that if two black holes did collide, that there would be these resultant gravitational waves. But, we say gravitational waves, and it's not like you're on a beach and you have this massive wave coming towards you. These are teeny, teeny, tiny little what we call perturbations. And so I really like the analogy you use. So the typical size of a gravitational wave is basically like you're saying the distance between.
Oh, the stretching. Yeah. Okay, yeah. So this is kind of crazy. So if you want to measure a gravitational wave passing through, it is stretching me up one way and making me thinner. So that sounds great. And then as the wave goes by, it squashes and fattens me out. If you're seeing that happen right now, it's because we've got a bad internet connection, all right? Or you need to get an antiviral software running. Something is happening to your screen. Because the gravitational waves, the amount stretching and straining is absolutely tiny, far, far smaller than the center, the nucleus of the atom. And in particular, if you want to measure these gravitational waves with something called LIGO, which we're about to go to see, you are having to measure something that is 1,000th of the diameter of a proton in the center of an atom. That's a crazy number. No one knows what that means. A better way to think of it is they're measuring the change in distance between here to the nearest star by about the width of that human hair.
Wow.
That actually really hurt. So, very,
don't try this at home.
Cool. Yeah, don't try that yet. So, okay, I think we built it up enough.
Yes. Right. So now let's go check out the detector that's making all of this possible. So navigate back to your home menu and now go down to LIGO. Now I want to quickly say that there's a lot going on in this because we've created a virtual laboratory for you to explore. So as we're talking, please notice that you'll see these little helpful white arrows that will direct your eye around to really important information about just how this works. So if we click on our first one here, for example, we can see again a summary of what we were just explaining. But then as we look further down, we'll see where the magic happens, so to speak. So what is LIGO? Now the short answer is lasers. But the longer, more
always the greatest thing to start with. Yeah.
But the more extended version is that basically because these little fluctuations are so small that we had to create an instrument that would be able to then help us measure that because we can't feel it. And so essentially they built these two lasers and they have to be on completely the arms of this detector have to be completely perpendicular and they're kilometers long. So
4 kilometers each.
As we explain this, so look down and you'll see your little detector here and you'll see some information about it. Now let's press the green button and turn our laser on. Well, wait a minute. You'll notice that laser just got split. So Alan, what's happening there? Why are we splitting up our laser?
Yeah, so this one laser has gone through that little black sort of slide of material. That is the beam splitter. So it's split into two. It's sent down these 4 kilometer long arms. It bounces off a mirror. Perfect mirror, by the way, made in Australia by the CSIRO. Oh, hey, Sale, thanks for joining us. Bounces off that mirror, comes back and forth. And basically, these two lasers are like super accurate rulers because we want to measure the change of their lengths. How do we do that? Well, that beam splitter shuffles one of the lasers half a wavelength out of phase. What that means is any sort of wave, including lasers, has a peak and a trough, right? You've seen that if you've drawn a wiggly line.
Yeah.
Basically, when there's no gravitational waves, when their lengths are absolutely perfect and not changing, when they meet back at the beam splitter, one peak fills in the trough of the other laser. So in other words, they cancel out perfectly. And that's what's shown on the little detector screen off to the right that's glowing with a little bit of static. For the kids who have not grown up with analog TVs, because you've got streaming and Netflix, that's if you haven't quite got the image in focus, ask your parents. So that static image, that's telling us that there's no gravitational waves. There's, a little bit of quantum mechanics jiggling around, so it's not canceling quite perfectly. What we're looking for is a gravitational wave, the stretching, straining of space-time itself, to come through, shift the arm's length of one relative to another. That's me getting stretched one way, but thin another. That is going to allow some of the light to survive, and that is going to be what's on the detector screen.
So what was so cool?
And we've got so many questions.
So wait, before we answer the question,
Jackie, just shout out. I am so sorry, everyone. Okay. Wow, where to go?
Well, first, before we jump to the questions, I think we should.
Should we finish this?
I have to say, we built this up. And so we've told you how it works. And this is probably going to fill even more questions, but that's all right. Okay. So we've told you how the detector works. And in your menu, you'll see that you can create two types of binaries.
Yeah.
Now, I want to point out that neutron star black hole merger happened before we finished, we finished doing the app. So we don't even have it on the menu.
You can't even update in time. This is how recent these discoveries have been made.
So
it's crazy.
Cool?
Okay.
But so I always love a good neutron star merger.
Okay.
So let's do the binary neutron star merger. Now, again, this might be where you want to drag your menu over so it's near the instrument so you can see what's happening as that merger is getting closer and closer together. And those gravitational waves are smushing and stretching space-time.
Yeah.
So you turn on the merger and you can see these incredible things called pulsars, which are a type of neutron star.
Yep.
Again, radio astronomy is how we're able to detect them. Yep. So now we look down and we see our lasers, and now you can see some stuff's going on with the lasers.
Yeah. The world is stretching and straining. The pattern is rapidly changing, and it's changing with the speed at which those pulsars or neutron stars are spinning around one another. Hey! And then exploded. I didn't expect sound. So we have so the two things are happening as that in-spiral occurs. The gravitational waves are arriving, and we can put that into a loudspeaker, those waves arriving. And that little rippling pattern you see, that sounds like very low at the start. So
it doesn't sound like a boom.
No, if you were very close to it, that's maybe what it could sound like. You hear a low frequency pitch. So, ooh, and then as they get closer in spiral, ooh, and then at the very end it goes, whoop. Not incredibly impressive, no. I will give you that. But what it signifies is the collision of two incredibly dense objects, absolutely shaking the very fabric of the space-time, the universe itself. In the case of the neutron stars, well, they do actually have material. You can see a neutron star, and that's indeed how we knew them. They were there to start with, through radio observations and everything else. But in the collision, the explosion, that is incredibly bright. That does shine in almost every wavelength of light, and it does something very, very cool in particular.
Yeah. So remember we were talking how everything we're made out of is made from stars. Well, actually, we learned that that's not the only way that heavier elements can be made. So as these two neutron stars collided, so much energy was released that some of these little atoms broke apart, and then other atoms were able to grab onto some of their protons and build up really, really heavy, really fast. And what I'm getting at is that they discovered that a planet's worth, so something the size of Earth's, that mass worth of gold was made.
And this is it.
Right there.
This is from a colliding neutron star pair at least 5 billion years ago, because that's when our solar system formed. So it had to be made before that to mix up and eventually find its way into a forming planet Earth.
It's amazing.
It's pretty cool. Okay.
So we're learning such amazing things. Obviously the gravitational wave detectors, we want to learn more about physics, what's going on with space-time, testing those laws. But then we're also learning cool things like, how do you make a planet's worth of gold? Just smash together two neutron stars.
Yep.
But we've kind of gone through a lot of the content we wanted to talk about. So now
we've got a load of questions.
We're going to get to some of your questions, and then we want to show you a couple other cool things on the app. So stay with us.
Okay, so we have a question from Aniket from Yarra Ranges Tech School. Can we study the mass of black energy using gravity? I think that's dark energy rather than black energy. So yes, you absolutely can. So dark energy is an unknown type of stuff that appears to be driving the universe to expand, but not just expand, but accelerate. So another way to think of this is, all those galaxies, their gravity should be pulling them back together, slowing down the initial impulse from the Big Bang. And we can then see an object like a distant galaxies. We measure their speed at which they're going away from everyone. Those galaxies appear to be moving ever faster away from each other. So they're expanding, but they're accelerating the expansion. So if I was to throw up the headset, it would come back down because there's gravity. I'd throw a bit further, come back down because there's gravity, just take a little longer. What we're seeing is that I've thrown it just a little bit further, and now it's hovering, and actually it's beginning to rapidly rise away from me. And the higher it gets away, the further it gets away from me, the even faster it's moving away. Very bizarre. We've called that thing dark energy, but we don't know. We have no idea. So yes, with gravity, you can try to do some experiments on the dark energy. To the best of my knowledge, we have used the gravitational waves to measure the shape of the universe in a crude way. We're getting better the more gravitational waves we get, and in particular, when we see their glow from other telescopes and combine that with the gravitational waves, we can really start to understand this dark energy. We hope, because right now it's a mystery.
Look, that's a great question, because we're talking about the major forces that we know that exist in our universe. We know gravity is the one that governs us, especially. But then again, thinking about what happens as we go further and further out. So I really like that you pulled those two things together.
Yeah. Okay, I'm going to throw this one to you.
Okay.
Sahasra asks, what is a space detective?
Ooh, I think we're all space detectives because we're scientists, okay? We're going out and we're observing, and we might find these patterns, or we might find some crazy object like a pulsar and just wonder, how does that even exist? And so in order to address that, we have to ask all these other questions and collect information. But I also think a space detective, so somebody that works at LIGO, for example, and we're getting these detections now, a few a week, they're really detectives because they get this signal. And then they have to figure out, is that a real signal? Is that really two black holes colliding? Or is that what we call noise from something else? Because again, that signal is so weak.
A passing car, a falling tree.
Yeah.
This detector is so sensitive, it picks up all of that.
Yeah, absolutely. So we have to ask, we can't just say, oh, I know that my detector works because I detected something. We have to work back and make sure that we understand exactly how that instrument is working and what should we be looking for. So
yeah, and you can be a space detective too. You can go to the Zooniverse website, so definitely to the teachers and parents as well. You can get involved. Head to Zooniverse. You have opportunities to look at galaxies and try to understand them and map them and help astronomers make discoveries. You can also use the Gravity Spy tool on Zooniverse to help us better understand the LIGO detectors. So the data comes to us, it looks weird and messy. Some things just don't make sense. Are they black holes? Are they these falling trees or passing cars? You can actually start to help us figure that out too. So get onto the Zooniverse. And okay, there's also some other stuff like involving, environmental causes and, animals and great stuff. Well, I'm more about the astronomy, but there's other great science.
I was going to say that's a good segue because, we're in this room right now, which is called the Baker Room. And it's where we're in Hawthorne actually able to control telescopes and talk to telescopes.
Oh, yeah, we should do that. Yeah.
And even in space. And so a wonderful space detective program is called Deeper, Wider, Faster. So if you have a chance, go to your menu and go to the Baker Room, and you're going to see this really cool 3D image put together by Carl, who's also on our awesome cyber team. And what's going on in this picture is our space detectives are looking for exploding stars in real time. Now, they're not just waiting to get an image and then thinking about later what it means. in the very seconds the telescopes are looking up at the sky, and we're taking that data and we're going through it to say, oh my gosh, do we see the signs of this mega explosion that could actually lead some of these compact objects that we're so curious about how they interact with space-time.
Yep.
So deeper, wider, faster. You guys can even at home join on that hunt in early December.
Oh, nice. Okay, cool. I'll have to book myself in. This is, just such a cool environment. The Baker Room is incredible to take 33 separate telescopes all at once, searching for the unknown. Very, very cool stuff. You can ask your questions using the hashtag AskSciVR, SciVR, and we will get the questions and we'll try to answer. Or the team of astronomers across the country will try when we fail.
Again, shout out to our team of astronomers that are online.
Okay. Oh, wait, no. Can you expand on the difference between dark energy and black energy? Okay, this is a follow-up question. I don't know what black energy is, but I think what was meant was dark energy. There is dark matter, but that's a separate thing entirely. And that's what I try to study.
Want to talk about, this is what. So I think it's really cool too for us to take a second. So Alan works with this amazing supercomputing facilities at Swinburne to simulate galaxies and learn how they grow. But he's also, like we were just talking about detecting gravitational waves, he's also trying to detect something that we thought wasn't really detectable and don't really know what it is. Yeah,
so there is an invisible type of stuff that holds the galaxies themselves together. It outweighs everything we can see 5 times over, but it is fundamentally invisible. It doesn't shine or emit light, absorb light. We call it, it's matter because it's got gravity, and we call it dark because, we can't see it because we're very creative that way. So creative. So dark matter. And in a project led by the University of Melbourne's Elisabetta Barberio, we are taking a dark matter detector. We are placing it at the bottom of the gold mine in Stawell, Victoria. And there in the darkness, we are waiting for this dark matter to slam into the detector and cause it to glow. That's kind of what I get to do as my job. It's so cool.
So before we answer some more questions, I actually have a challenge, especially for some of our younger audience members that might be out there. So we've been talking all about black holes, and somebody earlier was asking how do they form? And so we have an asset in SciVR. So let's go home on our menu. And if you go to Star Lab, now I'm just going to give you the instructions of how to navigate, and then I'm going to let you guys go for it as we answer some more questions. So Star Lab is this incredible, basically your mission control, your dashboard here into space. Now, as you look down, you'll see a few buttons. The red one is home. If you get a little bit confused, you can always click that to back out. Now, you'll see a cannon, but let's not touch that just yet. To the left, you're going to see 3 different paths. This is basically because we want to show you guys how what we call stellar mass black holes are formed, or even what would happen when a star like our sun dies. So I would say, let's go for the exciting one. Click the very bottom one that we see on the right is going to turn into a black hole.
Okay.
Now, if you click on that, you're going to look back above your cannon, and you're going to see a massive star.
Yep.
Now, if you click on that star, you're going to actually make it evolve. And eventually, boom.
Whoa, super red giant. Yeah.
Go supernova.
And boom, explode.
Hey. Into a black hole. Now, the challenge I have for you is to go down to your cannon, and you'll see that you have a little direction pad, so you can click on those arrows and change your cannon's aim. And then you can also click on that number and change the speed. But if you press the red button on the cannon, you're going to fire our particle projectiles at that black hole. Now, Mark, who's manning the camera, is obviously an expert at this, and he got the accretion disk in the first go. But,
so it doesn't fall directly into the black hole. Right. If you get it at the right angle, it will go and orbit
around. So you guys see if you can get it to orbit around, because I tell you what, it's much easier to fire it in the zone where that black hole is just going to grab it and hold on to it forever and ever and ever and ever.
Yep.
But if you can get it to do the accretion disk, then you figured out that special spot. So you guys give that a go, and I want to see if we have any more awesome questions that are coming through.
By the way, I don't know how you do that every time, Mark. This has literally gone straight in for me every time. Okay, so Banny has asked, what was the first planet made? So I'm guessing what was the first planet that formed in our solar system?
Oh, in our solar system. So the planets in our solar system formed over millions of years.
And but this is all billions of years ago.
Billions of years ago. And when our star, basically, there's a special point in our star's life when it turned on. That means it got hot enough and dense enough that in its core, it could smush together atoms, starting nuclear fusion, starting to radiate and emit light, but then it also casts away a lot of the material around it. Now, at that same time, we have what were called these little particles out in space, basically just little teeny tiny dust grains made up of carbon and iron and very dense materials. Now, those were dense enough that they could withstand the heat of our new baby star, and they could clump together. And so they were clumping and growing. And then once that started to happen, they could grow up faster and faster until planets like Earth and what became Earth and our moon, Theia, and even Mars and Venus, those came together. Okay, and those are the rocky planets. But just a little bit further out, past Mars, what we call the frost line, this is where it was cool enough for gases to come together and for the gas giant planets to grow and form. Now, we think that those gas giants had to form a little bit later, again, because things were so hot. But really, we think of it more as a distance. If you were closer to the sun, then that's where the rocky planets tend to form, just because it was so daggum hot. But then as you get out further, the gases can come together and grow very quickly and very rapidly spin up these gas giant planets.
So what was the first? Well, they probably all formed about the same time. But since Jupiter is the biggest, it probably had the head start in growing, so maybe Jupiter. Okay, so we have a question from Wagga. How do you calculate the mass of a black hole? I love this question. It's a great question. So there are two ways you can do this. The first is you can watch as things go around the black hole. So the faster they go around this object, and that can be a black hole, it can be the sun, it can be anything, the more massive, the greater the mass of the object is. So if you get something that goes very close to a black hole, it's going to be traveling incredibly quickly and almost about, a tenth to a third the speed of light by the last sort of lapse it's making. So when you do your gravity sim, if you could figure out the distance of that little cloud of material, how fast it's whirling around, those two things together will let you figure out how much mass, the gravity that's pulling the material around it. Fun fact, if our sun became a black hole today, our orbit would not change because all of that gravity is still the same, at least as far as we're concerned out in our orbit. The other way to try to figure out the mass of a black hole is to listen to it collide. The more massive the black hole collisions, the different, and indeed even the difference between them, the different sound, that chirp. I'm not pitch perfect, so I can't actually do this, but it will actually change the sound of the collision. So with that, you can actually figure out also the mass, and I mean like directly.
I think, don't we have a special image that we can put up to show the detections? So as you're talking to that. Now, guys, we only have a few minutes left, so send through one or two more questions so we can make sure we get to it. But as you can see behind Alan and I, so what's really cool is if you see the Earth, you'll see that this gravitational wave, this detection, was detected not just at one facility, but at two. And that's A, how we can confirm that it's a real thing, and B, so how we can kind of know exactly where it came from. And there's actually 3 facilities now. So we're even moving, not just in America, but going across the globe, and maybe one day even in space. I'm still waiting for that to happen.
Oh, yeah, Lisa. Yeah, that's a cool detector.
But you can see this cool graphic that's been put together. And again, as those massive objects come together, they just send out all this energy, and that then deforms space-time in waves.
Okay, so Brajnot asks, why is the universe always expanding?
It just doesn't know what to do. It just wants to keep going.
Yeah, I mean, from that initial Big Bang, we had all the material flung out. I don't want to say an explosion, but because it's not quite that, but it's not a terrible way to picture that early universe. So it's rapidly expanding out. Slowly over time, just like any explosion does, it begins to slow down. In this case, it's because the gravity of all those galaxies that are forming pull back on this expansion, slows down. But then, as I said, about 7 billion years ago, something took over and began to accelerate them away, and this is dark energy. Without the dark energy, would it have continued to expand, or would it have the gravity of those galaxies eventually overcome and started to drag each other back towards one another? So it's like the movie goes in reverse. They get closer and closer and closer, and then finally they crunch together in a single point. This is called the Big Crunch, the opposite of the Big Bang.
Very creatively
I know, we're amazing.
Well.
Yeah.
But yeah, so we have. This is a great question.
Oh, Perth. Why don't we build a gravitational wave detector in Australia? I'm heartbroken too. Yeah. Okay, so there's two answers. One is it's amazingly expensive, very, very expensive. About $100 million was the kind of the price tag. Now, to be honest, it would have been incredible if we had done it because, as Rebecca mentioned, we have those two detectors, the LIGO detectors in America, and basically, as the gravitational waves hit, it hits one and then the other, so you know that the wave came from that direction. Yeah. But it's a little unclear exactly where, and that's something you'll see in the gravitational wave events page. You'll see that glow on the sky, and that's we think it came from that rough direction. But if you have a detector in Australia, you are perfectly, like as far away as possible from those two, you perfectly triangulate, so you can figure out with the three exactly where did the gravitational wave come from. It would have been beautiful.
I don't think it's too late. We're going to have a dark matter detector. We've got some amazing radio telescopes. Why not have, a gravitational wave detector too? Now, I want to quickly tell you guys about one asset that we didn't delve into, but you guys are going to explore in your own time. But then I would really appreciate it, especially if our helpers at the library, we want to ask you all a few questions so that we can capture just how much you enjoyed the event and get a little bit, more information about whether you've ever been to, let's say, a National Science Week event before.
Yeah.
So very quickly, though, if you go back to your menu, you'll see an app called Bigger Than Big.
Yeah.
And we won't delve into this, but you can, when you go in, can literally delve into stars and just see a little bit about the scale of things, because we've been talking about the humongous to the very, very teeny. So please do have a look at that and explore all the planets and just go for it. But now, we really appreciate, you guys joining us today. And so we would like to ask you a couple questions.
All right. So to all of the volunteers and assistants everywhere, I guess you could try to video this for the next couple of minutes.
Just use your phone.
Yeah. So I'll give you a couple more seconds to set that up. Or just
count hands. So you guys
count hands or video.
These are yes/no questions. If you're a yes,
raise your hand.
If you're a no, you don't raise your hand.
Okay. First question. Have you been to a National Science Week event before? I'm looking around the audience. How's none of my team been? We were here. Yeah, very well, very well. Okay. Have you been to a Science in VR event before? So one of these. Yeah. Good to see everyone here is a veteran as well here. Okay. I don't think we'll do that.
No.
Let's go. Sorry, it was an age question. It would be rude. Did you enjoy the science in this presentation?
Woo!
Yeah, cool. Okay. Did you enjoy the virtual reality in this presentation? That's this. Yeah, I'm a big fan too. Would you attend a Science in VR talk again?
Oh, yeah.
Oh, sorry. Yes, no, I would. I would. Nearly there. Has this event made you want to attend another Science Week event? We've only got a couple of days, so get on to that. We have an online survey, so you can see that at the SciVR.com.au website, or the volunteers will be helping you fill in those forms. That's just a bit more details. Yep. If you do it, that's amazing. No pressure, but we are really grateful for all of your efforts.
Again, we want the concept behind this year was being accessible. So we love to hear your feedback. We love to hear what you want to learn more about. So please let us know. Oh, okay. I think we have one last question that I really want.
Cool. All right. So Evanston from Perth, there's three, and I'm going to really do them quick. Evanston from Perth, what's at the center of a black hole? Okay, all that material crushes, eventually forms a black hole, like the escape velocity is too fast, not even light can escape, so we can't see what's inside, but this is what we think happens. It keeps crunching. Nothing can stop it getting denser and denser, smaller and smaller volume, all the same mass. Eventually, all that mass into something the size of nothing. we call that a singularity, and that is where all the laws of physics breaks down.
If you're scratching your head, don't worry. Everyone else is too.
Yeah, because we don't know what that is.
Einstein couldn't figure this out, or Stephen Hawking. So we're still working on it.
Joey at the Gundagai Library has asked, how do new stars form? Well, this is where a cloud of gas slowly begins to condense. Its gravity gets stronger and stronger, pulls the material in. Those kind of gas clouds, that's the dark stuff that blocks the starlight. In that first picture we had of the Milky Way galaxy, the EU in the sky, deep inside those dark regions, new stars are being born, and eventually they'll blast that material out and will reveal themselves.
These are really cool when you can see in Orion, the constellation, even with binoculars.
Yeah.
So give it a go.
And Amy, 8 years old, thanks for telling me, from Yarra Ranges Tech School. So thank you for this. What is outside of space?
Wow, I love these questions.
Yeah,
you guys are really thinking just way outside. So we don't know.
Just more space. Yeah, there's no wall, there's no end edge. If you just kept traveling in space, you would still find more space. Is it infinite in size, or does it wrap around on itself?
Are there more universes?
Yeah.
I don't know. We might have to explore that next time because we are unfortunately out of time. Thank you so much for joining us and for asking such amazing questions and going on this fun journey with us, because we can't wait to talk to you again next year, because I can't imagine. We took a picture of a black hole. We've detected heaps of gravitational waves. Can you imagine what we'll be telling you about next year? So thanks so much.
So thank you to all of you for joining us, and thank you to Swinburne for hosting us, for Osgrav, the ARC Centre of Excellence for Gravitational Wave Discovery, for making all of SciVR possible. Thank you all to who's in this room, and of course volunteers from across the nation and into Sarawak. Thank you for making this all possible. And of course the Inspiring Australia National Science Week grant. Without your support, none of this would be possible. So with that, have a happy remaining Science Week. And if there's nothing else on in your area for this year, well, make sure to sign up for the stuff that's on next year, because these things are the happiest time of the year. And they come every year, just like Christmas, but, more for geeks.
And you can explore your app as many times as you want. And please check out the website, because we'll put the recorded version of this talk there. All right, guys. Thank you. We're going to sign off. Cheers. We did it.